we are going to think about composite functions and graphic transformations. More specifically, we're going to think about horizontal stretches, okay? So you know that the function sine of x gets smaller when you do sine of 2x. There's a whole thing with the horizontal axis doing everything backwards as to what you expect it to do. I have also a video about that. But for today, we are taking this for granted, right? If it was x over 2, then the function gets bigger. But today, I don't want you to just think of these things as graphic transformation, horizontal stretch, simple like that. I do want you to think about this as a composite function that has the sine of x on the outside and the 2x on the inside, or the x over 2. Of course, these two functions are lines. 2x has a bigger slope than x over 2, and that is basically what's going on. 2x makes the function go around faster because it's faster. It has a bigger slope, right? The other one is going slower with a smaller slope. So when you put that inside of the sine function, that makes the sine function go slower, which is what makes it look bigger, like it's been stretched. And when you understand things like that, you can start to do other different composite functions which are not in the syllabus, in the sense that, of course, any composite function is in the syllabus if you're only going to handle it algebraically. But understanding the graphical effect of a composite function that is not just a linear function on the inside, that is not in the syllabus. That doesn't stop us exploring what happens with that. For example, x to the power of 2 is not a linear function. X to the power of 2 starts out very slow and then it goes faster and faster. So what do we think should happen if I type in sine of x squared? What the 2x and the x over 2 examples are teaching us is that when the slope of the function is small, it goes slower. And when it's a big slope, it's going to go faster. So in the case of x squared, which starts with a small slope and then gets bigger, I think it's going to start by going slower and then it's going to speed up. And that's exactly what sine of x squared does. Look, it speeds up more and more and more the more you go to the right. This is not a periodic function, okay? You could ask for other things. What about 1 over x? 1 over x is the opposite. It starts with a very steep slope and then it goes down. The slopes in this example are negative because the 1 over x function is decreasing, but it's not going to matter because the outside function of our composite is a sine function, which is all periodic. So when we're looking at a decreasing function inside of the composite, all that matters is that we're moving to the left in the sine function instead of to the right. But visually, that doesn't matter. It's going to look exactly the same. So sine of 1 over x is kind of the opposite of the sine of x squared, right? Because the slope is getting very small in the end, so the function is slowing down. You can see that it's not even oscillating anymore as you go to the right. It's just flattening out. And over here in the middle, something very bizarre is happening. It is speeding up more and more, but because the slope of that function is going to infinity, right? 1 over x has a vertical asymptote. So it wants to go infinitely fast, which means that if you open it up like this, you can still see some of it going faster and faster, but at some point you stop seeing them. It just looks like a painted area because it's going so fast. Another interesting example that the most curious students sometimes ask, like, what does it look like when we start doing composite functions algebraically, right? So for example, sine of cosine of x. What does that look like? Well, it looks periodic, but you see how it's differently periodic? It's more rounded on the top than the usual sine function is. Also, its maximum is not quite at 1, because what's happening in this case is that you kind of have to think about domain and range of the inside function and the outside function of the composition. So with the cosine inside, cosine only goes between -1 and 1 for range. So the numbers that are going inside of the sine function are only numbers between -1 and 1. So between these two vertical lines here, so the outside function keeps going back and forth between these 2 points. And that's the value of the function. It's not quite -1 here. It's not quite 1 there. So that's what the blue function is doing, which is sine of cosine of x. So here is another interesting example. I am going to start with sine of 10x for my outside function because it oscillates kind of fast. But what I wanted to do is that I don't want it to oscillate forever. I wanted to do a little bit of its thing here and then level out on both ends. So my question is, what do I want to put inside of it for that to happen? The answer is that around the middle, I want something that looks pretty much just like y equals x, because if you put just x inside of a composite function, it's the same thing as not doing anything, right? So around the middle, I want it to just look basically like x, so that the outside function is going to continue to doing what it's doing. But then after that, I wanted to level out two asymptotes, which are horizontal, so that if that is happening in the inside function, the outside function is going to stop moving as well. So the question here is, what function do we know that does that? Starts with an asymptote, comes back up, and then flattens out again. Yes, arctangent. So there you go, sine of 10, arctangent of x. Look, it's kind of exactly what I was describing. It oscillates in the middle and then it levels out. It has a last local maximum here, and then it's going to go down again, but very, very slowly. Where is that horizontal asymptote going to be? Well, you have to think of domain and range again. Inside, we have arctangent, which was going to pi over 2. And then it's multiplied by 10, so that is 5 pi. That is where the sine wants to go to, the sine of 5 pi, which is 0. So this purple function here is going to have 0 asymptotes on both ends. So I hope that was enough examples to explain the kind of thing that I'm thinking about. Let's go back to thinking now about our function to see if we can do the one that we actually want, okay? This next example is going to require a little bit of context as to what we are trying to do, because this video is a part of a larger video that I'm going to post next, in which I am writing an IA. So there is a context, there is a function that I'm trying to build, but for now I'm just going to show it to you here, like this is where we are trying to go to. And then later, if you want to see the whole context, why I'm doing this, where this comes from, just watch the next video, which is going to be the full IA. So what we want is something that oscillates and then pauses, and then oscillates and then pauses, and does that periodically, right? So what do we need from our inside function of the composition for that to happen? We need for it to be increasing and then pausing, and then increasing and then pausing. So it's like increasing line and then horizontal line, increasing line, horizontal line. Do you know any function that does anything sort of like that? If you start from the sine function itself, you know that the derivative is kind of like 1 here and kind of like -1 here. So again, 1 and -1 and periodically. So if you add that to x, it becomes 2, 0, 2, 0, 2, 0 instead of 1, -1, 1, -1, and so on. That is the function that I am thinking about, that sort of thing, right? Of course, I'm going to have to adjust parameters, but something that goes up and then pauses, up and pauses. That's going to be the inside function. If I use the sine of 10x as an example here, as an outside function, this is kind of what's happening, right? It's doing its thing and then pausing, doing its thing and then pausing. I'm just going to have to adjust the parameters so that it does exactly one loop and then pauses, and then one loop and then pauses. Okay, so here are some numbers that I want to write down. 15.02 is where I wanted to start going up. And then at 18.3, which is the beginning of the second loop, it's already started going up and stopped going up and paused, and I wanted to start going up again. But then I don't want it to look like P of 18.3 because that is not the period of P. The period of P is smaller. So I want it to look like P of 17.1, which is where it would naturally have started going up again. But I want to make it wait and then only start going up at 18.3. So what I'm going to need is a function that is sort of like sine of x plus x, but I'm going to stretch it and move it around so that it not only goes through those 2 points a and b that are just the numbers that I just said, but it does so in kind of the way that I just described, right? Which is like start going up here, and then at some point you're going to pause and start going up again there. This is what I wanted to do. Okay, so now let's see the results. I have a bunch of different functions because I didn't want to do all of the graphic transformations at the same time because that would be confusing. So I started with just sine of x plus x, which I called t. And then for s, I did the horizontal stretch and the vertical stretch required on t for the periods. So remember, we have two different periods here. One in the horizontal, which is 328, is the period of the function that I want, which is what the 2 pi over 3.28 is doing there. And on the vertical side, we have a different period, which is of the original p of x function. Because vertically, as we move from point A to point B, we're not supposed to be moving 3.28, but only 2.09. So that's what this other factor of vertical stretch is doing outside here. And notice that it's upside down because of the difference in how the horizontal and vertical axis handle stretches. So after the stretching, the function already has the correct size, but it's not necessarily going through the points. So this other function v here is just the vertical translation. I subtracted wherever it was on 15.02 and then added 15.02 because that's point A, it's 1515. So this is the result, the same kind of function, but now passing through points A and B. So there was no guarantee that after I did the stretches and the vertical translation, of course it would pass through both points, but that was intentional. But it wasn't guaranteed that it would pass starting on the going up. It could have been anything. Point A could have been in the middle of the going up, for example, or in the beginning of the more horizontal part. As it turns out, however, it's not too bad. Point A is kind of in the beginning of the part where it goes up. I wish it was a little bit later, but this looked good enough to try already, and I still have a horizontal translation that I can make if it doesn't fit the points very well. So the picture that I'm showing you here is already with the horizontal translation that did turn out to be necessary. It was x plus 0.33, and it looks absolutely great. I am very, very satisfied with this result. At first glance, you could say that the horizontal part is not nearly as big as the one that we had with the piecewise function. But then again, look, it's passing through that point over there almost perfectly. And the same kind of thing is happening on the second spin. So I'll just mention one more thing about the 0.33 number, and then I'll tell you how you could try to improve this result. So 0.33 was basically trial and error. I looked at the picture without the horizontal translation, and it was clearly shifted to the right. I could have just chosen a number visually, but instead I went back to the sine of x plus x, and I tried to shift that to the left in order for the point A to be like closer to the beginning of the rise. So I put this orange line here, which is just the line y equals x. Remember, point A is on the line y equals x because it is 15.02 and 15.02. And that's what we want for the beginning of the spin, right? We want the function p of x to be just p of x and not p of something else, because at that part, it was doing the spin like we wanted to. So the closer that I can get my inside function to match y equals x at that part, the better. So I put y equals x in orange here in the picture and just chose the horizontal translation to get as close to that as possible, and it turned out to be 0.33. Notice that when I did that, the red function is not exactly going through the points A and B anymore. It is a very slight shift because 0.33 is such a small number, And there were ways that you could try to fix that in a different way. Basically, when I had a bunch of steps in building that function, you could have done the horizontal translation sooner. That's something that I don't want to think about right now, but if you want, as an exercise, I did the horizontal translation on V. So maybe if you did it in S or T, you could try to visually match it to y equals x in such a way that it still passes through both points. That is something that is worth exploring and exercising in case you want to build your skills in doing that kind of thing with functions. And the other thing that I would suggest, if you want to make it even better, is that when I remembered about the function sine of x plus x that goes up, horizontal, I didn't really try at all to say for how long it should go up and for how long it should be horizontal. I just allowed it to do whatever it wanted. And lucky for me, that turned out to be a very good result. But you see that the horizontal part is shorter than we wanted it to be. So maybe you could try to change the sine of x plus x function in some way so that you have control over the length of both types of parts. I would actually really like to see somebody else come up with an even better function to fit these points. So if you do that, please let me know. Just tell me the final result. What function does this even better than these? So like I said before, this video was part of another video. This was the mathematically challenging part where we actually needed to learn how to do something new that you maybe had never done before. But I did that for a reason. I did that as part of an IA in which I was trying to do something. So that is going to be the next video that I'm going to post. And if I've already done that, then here is the link. You can click and go watch it.